Good morning. I will show you, I will give the lecture on logic synthesis. So logic synthesis is in a CAD tool flow, logic synthesis is a major step which is essential. So in logic synthesis, the basic problem is to convert from Boolean equations or a gate level netlist to a component level design. You may have a Boolean equation or you may have a finite state machine for the system. For example, I have shown there are actually two forms of specifications. One is called PLA and another is called sum of product specification. In sum of product specifications, we add some product terms and specify the logic equations, and in PLA you can see that I3 means in 3 inputs, O3 means 3 outputs, and P4 means there are 4 product terms, and there are 2 planes. One is the odd plane, first one is the AND plane, and the second one is the OR plane. Using the AND plane and OR plane, we specify the functions. Text please. Now this is the PLA representation. You have 4 product terms and you have 3 inputs. This is called the AND plane. Now X means there is no connection, 1 means it is connected to the A or A bar, A, and 0 means it is connected to the A bar, and similarly for B and C. Now for this representation we will connect what? For the first one we will connect A and C. For the second one we will connect A bar, sorry, for A there is no connection, B bar and C bar. For the third one we will connect A and C bar. For the fourth one we will connect what? B and C. This is called the AND plane. This is the OR plane. This is the output X, this is the output Y, and this is the output Z. For A, X we have only A C bar, so only we will connect this, and for Y we have AC plus B bar C bar plus BC, so we will connect which one? AC plus B bar C bar plus BC. And for Z we have AC plus BC. So this way we represent the Boolean functions, and in sum of product form you all know it is very straightforward to in sum of product form it is very straightforward to express the function. Now the logic synthesis problem is to simplify the logic equations, reduce the number of literals, reduce the number of operands, and map the logic equations to gates. Suppose AND gate, OR gates, or flip-flops. Flip-flops we consider as a single block. And gate level optimization, we replace the OR NOT gate by NOR gate, etc. we will have we can have several goals, suppose delay, power or area, but see these goals are conflicting to each other. Suppose if you want to minimize the delay, then the area will increase and vice versa. So we have to take some in between stages to optimize the area, power and delay, all these things. And technology mapping we will not discuss in this class lecture. Now, two level logic minimization, the PLA kind of things are two levels. Since there are two levels, one is AND plane, another is OR plane. So this is called two level logic. In two level logic minimization, the first thing we will study is Carnot. I think most of you have already gone through Carnot. In Carnot, it's a truth table representation like things. There are 2 to the power n entries, and there are 2 to the power n number of entries for a logic equations, and we'll try to cover them using cubes. Suppose, for example, if suppose f equal to if this is the f, then we can have a Carnot map corresponding to this. We will cover the min terms. These are the min terms a b bar, suppose this one. Then we have c. C means all these 4. Then a c b bar. A c b bar, that is already covered. So we will cover these min terms using cubes like this and this, and we will get the minimized function as c plus a b bar. Okay, this way we use Carnot map. For Carnot map, the disadvantage is we can maximum take 4 or 5 variables. But suppose we can have 50 variables, then there will be 2 to the power 50 number of inputs in the 2 to the power 50 number of blocks in such Carnot map. That is totally infeasible to do in practical situations. So we can have some algorithm to minimize the logic. Carnot map is not a very good algorithm to implement on a computer using some software applications, because we visually see the things and encircle the min terms. But in case of computer CAD tools, we have to use some automated algorithm to minimize the logic. So we will discuss one algorithm such. This is called espresso. These are the problems in Carnot map. The number of cells in is exponential in the number of inputs. Suppose for 50 input circuits, 50 number of blocks, and for computer applications we must have some data structure which will automatically do the things. Espresso in one such algorithm which do the 2 level logic optimization very efficiently. See, espresso is not an exhaustive algorithm. It do not searches all the min terms and extract the global optimum solutions. It is a heuristic kind of approach which iteratively refines the solutions and try to go to a suboptimal, maybe what is good enough for our purpose. This kind of solutions. This type of algorithms are called iterative refinement algorithm. So we can have a Here one concept is coming, hypercube concepts. Suppose we have three variables a, b and c. For three variables we can have a hypercube of this kind. Suppose this is the a direction, this is the b direction, this is the c direction. Now we encircle, this is the 0 0 0 point, this is the 0 0 1 point, this is 0 1 0, this is 1 0 0. Okay. Now whichever are the min terms in this cube, we will encircle them. I will show you the slides. For here I have shown for two variables a and b. Suppose a bar, b bar and a b bar are the min terms for two variables. This is the hypercube. We will encircle the a bar, b bar and a bar b. This is called a cube that we encircle. Okay, for in this kind of situations, suppose in the function I have shown just now, a bar, b bar, c plus ac, b bar, we will have, let us take some another function. Suppose f equal to a bar, b, c bar plus this point is 1 1 0, b bar, c bar, a, sorry, bc plus abc plus a b bar c. Suppose this is our function. So we encircle these points in the hypercube. This is one point, this is one point, these are the 4 points, and suppose a bar bc, this point, sorry, what's this point, a bar b bar c, a bar b bar c, this is a don't care point. Okay, so we can encircle this one also. This one is a don't care point. So we will encircle the adjacent points in the hypercube. So this one is a cube, this one can be a cube, this one can be a cube, this one can also be a cube. Since this is a don't care term, we can encircle that. Okay, the basic approach you can see. Yeah, cube means you are encircling two or more, 2 to the power in terms of on terms. Okay, these are called cube, these are not cube shaped. Okay. The basic approach is you can see. Yeah, you can circle that. You can circle that. In the algorithm, you will iteratively do that. It's not you can see, visually see and think that these 4 can be encircled in a single step, but the computer do not know, no? So it will iteratively refine the things and gradually go to the optimal position. So the basic approach is you have on states, set of vertices which corresponds to one min terms, 1, and set of minimum set of cubes, and size of the cubes may be increased by exploring don't care literals also. See, this is the basic algorithm for espresso. R is the offset, D is the don't care set, and F is the onset. So sorry, the first one is the onset. There are 3 steps: reduce, expand, and irredundant. I will show you the 3 steps in detail. Okay, and this is the expand step. In expand state, what we do, we encircle small hypercubes, small on terms. Then we try to expand the on terms depending on the what are the adjacent on terms to that on terms. Suppose in this case you have 1 is the on term. 1 is the on term, and adjacent to that, first we encircle 1 then we see that adjacent to that 101 is another on term. We will expand that 111. Then again what we do, we see that 110 and 100, these are the adjacent to this cube. This cube is adjacent to this cube, so we will encircle that whole things again. Okay, this way we will gradually expand the hypercubes and try to see what is the maximum possible encirclement of the on terms and also the don't care terms. So this is the expand state. Now irredundant state. After expanding, we may have got some irredundant cubes. Suppose in this case, I should have clearly. Don't care terms means so whose values you do not care, what that may be on or off, you don't care.
So that is given in the expression itself.
Or we decide
With the expression.
Yeah.
Or we decided on.
No. Okay, suppose we first encircle this, then encircle this, then expand this to encircle the whole. Now in irredundant state, what you do, after encircling, after expanding the things, you see that some what happened in the after expanding, you see some cubes are irredundant. Are redundant. You just remove those cubes. Suppose here this cube is redundant, this cube is redundant. You just remove those. I can take a better example. Actually, this example is not showing the things properly. Suppose you have this encirclement, you have this encirclement. Suppose you have this encirclement and you have this encirclement. These 4 encirclements are there for another function, suppose. Now after expanding these things, you see that these two cubes are not required at the same time. One of them will suffice. Suppose if you remove this, you will also cover all the on terms, or maybe you can remove this. This is the irredundant state. You will remove the redundant cubes. Suppose you remove this. The next step is the expand step. Sorry, reduce step. In reduce step, what you do? This is the irredundant step. You throw out redundant cubes. Okay. Now in the reduce step, you do a funny thing. You will do the reverse. You can't see the. Okay, slides please. Okay. In reduce step, you will do a very funny thing. You will do exactly the reverse what you do in the expand step. You will try to minimize. You will try to minimize the cubes. Suppose you have this cube in the after the After the redundant step, suppose you have got these 3 cubes. Now what we do in the reduce step, you will just make 2 out of this and remove this one. Why this type of things are done? This is to such that you do not stuck into a local minima. This is called simulated annealing. Simulated annealing, I don't think most of you will know. Simulated annealing is a iterative refinement algorithm. What it do? We just don't always take the best term. We don't always take the best move, but sometime we also take the worst case also. Okay. In the initial stages, but later on when time progresses, we will reduce this time. We will reduce this kind of operations generally. This one perturbation will also do. This is called perturbations. That is what I was telling just now. That we.
What is the use of that? The redundant state is becoming
Yeah, reduce step is done because suppose some other in other direction. Suppose you can have get some bigger block, okay, that you have not got in the previous expand state. Those cases reduce state will help. It will reduce the cube to unit blocks and expand in other directions. This is I am showing this for only 3 variables. It may be for many number of variables, 50, 60 variables. For other directions, there may be expanded to a better solution. Okay, this is a heuristic kind of thing. This is not a straightforward approach. Just you do in Carnot map, you just see and encircle things. It's not like that. Okay, in perturbation step, what we do? We just arbitrarily add some extra min terms which do not change the function, and try to do the rest of the things again iteratively. In perturbation is the same. Perturbation is done for the same need. Okay, now we will be able to understand the algorithm. This is the algorithm. Okay, you iteratively do reduce, expand, and redundant on F and don't care terms to get the optimum solution. The algorithm can stop when your time bound is reached. That means suppose you want to run the algorithm for 10 minutes and 10 minutes is reached, whatever is you have got, that is you will consider as optimum. Means it's not, maybe it's not the optimum, it may be the suboptimum, but you will consider for your unit that is optimum. And there may be another termination condition when there is no change in using these operations, iterative operations. So this is the end of espresso algorithm. This is the end of espresso algorithm. Now I will see for sequential logic minimization, what are the algorithm to minimize the logic. For sequential circuits, all of you know the sequential circuits are combinations of combinational circuits and D flip-flop. There is a combinational block. There are some inputs I. There are some outputs. There are some next states. These are the flip-flops. All of you know this, that this way sequential circuits are realized. Now, sequential circuits can always be Sequential circuits can always be represented using a truth table kind of thing. Now, what is the motive for minimizing the state machines? Using FSM, and FSMs are can always be represented using truth tables. Now, I will show you what is the need for sequential logic minimization. Suppose you have a state machine, you can have a number of states which are equivalent. What is before that I will define something, that what is called equivalent and what is called suppose you have a state machine. State machine is a directed graph which is a tuple called S naught, then there is transition, there is a transition function and outputs. Okay, S are the, this is the formal definition of a finite state machine. S is the set of states, S0 is the set of start states, maybe 1. T is the transition, T is a subset of X cross S. Okay, and delta is a transition function. That means delta is a mapping from S, and there are some input also. I are the input alphabets over the output alphabets. Okay, and I are the input alphabets, O are the output alphabets. For our case, we will consider only 0 and 1 as input and output alphabets. Now, what is when we call two states are equivalent? We will call two states are equivalent if for a input sequence X, if we apply for Si and Sj, if we apply input sequence X, if it will produce the same output sequence Y, then we will call that Si and Sj are equivalent. And what is distinguishable then? If suppose we apply some input X and we get some other input Y, then we say that Si and Sj are distinguishable. Now I will define K. What is K distinguishable? K distinguishable. Suppose in a state machine you have two states, Si and Sj. Si and Sj, and you apply input of length k. If input of length k will determine that Si and Sj are not equivalent, that means they will give you different output sequences, then you will say that Si and Sj are k distinguishable. And similarly k equivalent, if input sequence of length k will give you same output sequence, then you will say that Si and Sj are k equivalent. Now using this distinguishable, k distinguishable, this concept, we will do the state minimization. We will see the state minimization algorithm. Why state minimization is required? What is state minimization? Suppose you have a machine M1 and you have a machine M2, state machines, and for M1 for every states Si belongs to M1, there exists a state Sk belongs to M2 such that Si and Sk are equivalent. Then you will say the M1 and M2, these machines are equivalent. You got the point? Okay. So for every states in M1, there is a state in M2 which are equivalent. This is the definition of two equivalent machines. So the state minimization problem is the problem to find a equivalent machine corresponding to a state machine which have minimum number of states. Okay. This is a state minimization problem. To show the state minimization algorithm, we will see an example. I will show you two state minimization algorithm. One is top-down approach and another is bottom-up approach. Okay, this is a state machine where present states are denoted by this column, and x equal to 0 means this is the zero successor of these states, and x equal to 1 means these are the one successor of these states. These states can be shown in following way. Suppose for A, if the present state is A, for 0 you will go to E with a output of 0, and for input 1 you will go to D with a output of 1. For B you will go to F with output of 0, and for input 1 you will go to D with output 0. Similarly for C, D, E, F. This way we represent the finite state machine in a truth table form. Now we will discuss the algorithm to minimize this state machine. See, this is the top down approach. Here we first assume that all states are equivalent, then gradually we refine the things and see which states are not equivalent and partition them out. Okay, so first we assume that all states are in the same partition. Okay, now there are 6 states. Okay, now what is the first one? Try to see whether which of them A, B, C, D, E, F are one distinguishable. See, you can readily see that A, C and E, if they are given input 0, we cannot distinguish between A, B, C, D, E, F, any of them. But if we give input 1, we will get one output for A, C and E, and we will get 0 output for B, D and F. So we can readily say that A, C, E, sorry, there is one mistake. Yes, C is 0. Okay, we can readily say that this is not a mistake. I just taken the example. We can readily see this, say that A, C and E are of one group, and B, D and F, they are of another group. Yeah, sure. See, first we assume that all of the states are equivalent. So we'll make a single partition of A, B, C, D, E, F. Now we'll apply one bit input, and see which of the states are giving different outputs. Okay, so we can see this is the one distinguishable thing. So we can see that A, C and E, they give with x equal to 1 input, they will give 1 1 1 outputs, but in conflict B, D and F, they will give 0 outputs. Okay. So with the input 1, A, C and E will react the same way. They will always give 1 output. But B, D and F will give 0 outputs. So we can readily say that ACE and BDF, these are of different sets. Okay. Now we will go to the next successor. From ACE we will go to the next successor and see and try to see whether they belong to the same block or not. Okay. From ACE, suppose from A we will go to E and sorry, we go to E with input 0, and for C, for ACE I am taking together. For ACE we go to EC, E and C with input 0, or for input 1 it will go to the D, B and F with input 1. Okay. Now with input 1. So what we say, I have some mistake again. Okay. A, C, C, D, B, F. Okay. And for BDF, we go to FC, FB with output 0, or we go to, for one input we go to D, B, C, okay, with output 1. But you see that for F we go to C, but C and DB are belong to different blocks in previous line. Are you understanding? No. Okay. For A, ACE or BDF are different. You understand that? Okay. For ACE, if you apply 0 input, x equal to 0 input, then we go to either to E state or C state. You can see from the truth table. For A you go to E, for C you go to E, and for E you go to C. So either you go to E or C with the output of 0. And for x equal to 1, sorry, for this one, x equal to 1, you go to D, either you go to D for A, or you go to B, or you go to F with output 1. So D, B, F are belonging to same set in the previous step, and EC also belong to same group in the previous step. So you can't distinguish between AC and E from this. But from B, D and F, if we apply x equal to 0 input to B, D and F, so where it will go? It will go to F. For B it will go to F. For D it will go to again F, and for F it will go to B. Okay, with the output of 0. And if you apply x equal to 1 input to B, D, F, these states, then what will happen? For B it will go to D with output of 1. For D it will go to B with output of 0, and for F it will go to C with output of 0. Okay. Now see, for x equal to 1 input, it will go to D, B and C. But you see in the previous step, B and D belong to one group in a partition, in the partition, but in C belonging to another group. So they are two distinguishable. So you can readily distinguish C with A and E. Okay. Sorry, got it wrong. C is coming due to F. You will readily distinguish BD with F. Okay. So this is the refined partition after 2 steps. Now you go to the third step. Okay. First step, what it will do? You will do in ACE you apply x equal to 0 input and x equal to 1 input again. For ACE you will go to EC with 0 outputs. For x equal to 1 you go to BD, DB and F with x equal to 1 output. Now see, D state is coming due to the state A, B is coming due to the state C and F is coming due to the state E. Okay, see, F is the one successor of E. Okay, but here you can see that DB they belong to one partition in the previous step, but F do not belong to that partition. F belong to some other partition. So we can readily say that E is distinguishable from A and C. They are how much distinguishable? 3 distinguishable. In the first step it is 1 distinguishable, in the second step they are 2 distinguishable, here they are 3 distinguishable. So we can readily see that AC belong to one partition, E belong to another partition, BD belong to another partition and F belong to another partition. Okay. Now for AC. AC what you will do? For AC, if we apply x equal to 0 input, you go to either in E, for both the cases you go to E, A and C, and for x equal to 0 input, 1 input, you will go to B or D, with the input of output of 1. Okay. The E you cannot refine further, it is already one element. For BD, you can refine BD using you will see whether you can refine BD or not. You will apply x equal to 0 input and x equal to 1 input to BD. For BD, you will go always to F with 0 input, and for x equal to 1 you will always go to either D or B with a output 0. Okay. So you will see that BD belongs to same group in the previous refinement, and also here BD belongs to the same group in the previous refinement. So you will see that after 4 refinements you will get the same thing, AC, E, BD and F. So this is the if you refine it further it will go, if you go on refining it you will always get this, you can't refine it further. So this is the minimum possible state that you can get. Suppose you name them, suppose this is S1, this is S2, this is S3. Can you see the last one? And this is S4, and from here you will get the state transition table as present state, next state and output, S1, S2, S3 and S4. For S1, AC is in S1. So what you will do, for A and C it will go to E. S1 is AC. See, AC, this is E, this is BD, and this is F. Okay, so from S1 you will go to S2 with a output of 0. For x equal to 1, you will go to S3 with output 1. For S2, C belongs to S1, you go to S1 with output of 0, and for 1 you go to S4 with output of 1. Okay, from this one you are taking this S2. For S3 is B and D together, so for S3 you will go to F belongs to S4 with output of 0, and for 1 you will go to D, that belongs to S3 with a output of 0 again, and for S4 you will go to state 3 with output of 0, and here you go to S1 with output of 0. So this is the minimized state transition table for this one. This one is the minimized state transition table for this one. You got the approach. Now we will do the same state minimization approach for using another algorithm. This was the top down approach. Now we will see the bottom up approach. Okay, this is somewhat straightforward, much easier to understand. Here we will compare the states. Okay, now we will compare the states and see whether they are equivalent or not. We will compare first, suppose A and B. Are they equivalent? They are not equivalent, because they are producing different output for same inputs. For x equal to 1 they are producing different outputs, so they are not equivalent, A and B. Now you go to A and C. You can't say whether they are equivalent or not. A and C will be equivalent if B and D are equivalent. You can understand? Okay, A and C will be equivalent. See, this A and C will produce the x equal to 0 successor is E and output is 0, and x equal to 1 successor is B or D. So A and C will be equivalent if B and D are equivalent. So we will say A and C will be equivalent if B and D are equivalent. Now A and D, are they equivalent? They are not, because they are producing different outputs for same inputs. Now we will see whether A and E are equivalent or not. A and E will be equivalent if C and E are equivalent and D and F are equivalent. Okay, are you getting? D and F are equivalent. Now you try to see whether A and F are equivalent or not. They are not equivalent, because they are producing different output for same inputs. Okay. Now you will see B and C. Are they equivalent? They are not. You can readily say that they are producing different outputs. Now you do for B and D. Are they equivalent? They will be equivalent if B and D are equivalent. B and D are equivalent if B and D are equivalent. Okay. So what it will say, B is producing for suppose input 1, B is producing D, okay, and D is producing B, and this will keep on going like this. So we can say, readily say, these are equivalent. Okay, so B and D are equivalent. Now see for B and E, whether they are equivalent? No, they are not equivalent, because they are producing different outputs. Now see for B and F, are they equivalent? See, they will be equivalent if B and F are equivalent or and C and D are equivalent. Okay. Now go to the third line. You compare whether C and D are equivalent. C and D are not equivalent because they are producing different outputs. Now try to see whether C and E are equivalent or not. C and E will be equivalent if C and E and C will be equivalent and B and F will be equivalent. E and C you can readily say, but B and F you can't say. Now you go for C and F. Are they equivalent? They are not equivalent. Okay, now you go for D and D. Are they equivalent? They are not. Now you go for D and F. Are they equivalent? They will be equivalent if B and F are equivalent and B and C are equivalent. Now you go for E and F. They are not equivalent. Okay. Now the first round is over. Now you do the same thing for the next iteration. In the next iteration, what you do? You go to this block. You check whether B and D are equivalent from this table. You can see that B and D are equivalent. Okay. So you can readily say this is equivalent. Okay. Now CE and DF are will be equivalent. A and E will be equivalent if CE and DF are equivalent. See whether C and D are equivalent or not. C and D are equivalent if BF is equivalent, and D or F are equivalent or not. See, D and F are equivalent whether when BF and BC are, you can't say this. Okay, in this point of time. Now you see for this whether BF is equivalent and CD are equivalent. You can readily say that CD are not equivalent. Here the cross is there. Okay, so you can readily say these are not equivalent. Okay, and for the next case B and F, you can say that B and F are not equivalent. Just in the previous line you have got that. So these are not equivalent. Now you see F and D will be equivalent if B and F are equivalent and B and C are equivalent. B and F are not equivalent, so this is not equivalent also. Okay. Now you see for this case, you again do the same thing. Since one block is left, so you go there, you try to see whether C and E are equivalent and D and F are equivalent or not. You see C and E, they are not equivalent. So you can readily say this block is cross. They are not also equivalent. So what you have got? You have got only A and C are equivalent, B and D are equivalent. So this is the same result that you got in the previous case. You got A and C are equivalent, B and D are equivalent. So for this case also you will get 4 states: A, C, E, B, D and F. Okay, these are the two state minimization algorithms approach for finite state machines. I will do one more example. Okay, take this one. See, this example was for a this example is for a milli machine. We'll do the same thing for a Moore machine also. All of you know, I think, milli machine and Moore machines. You don't know? Okay. Milli machines, there are inputs and outputs, but in case of Moore machines, there are no outputs. Okay. There are final states instead. You can find the formal definitions of these machines in any automata book. see the two algorithm I just discussed, these are for completely specified finite state machines. There may be some machines which are not completely specified, incompletely specified finite state machines. For those I do not discuss. Okay, those who are interested, they can go through. Completely specified means for every inputs and for every inputs the next states and these things are known. Okay, so this is a mode machine which has 6 states, 4 final states, and we will show which of the states are equivalent and which are not. So we can readily find out the state diagrams. These zeros and 1 indicates whether the states are final states or not. Okay. So what we can do, we will consider Z is the output which specifies whether Si is a final state or not. See, S4, S5, S6 are final states, so the outputs are 1. Okay. Now what we will do? We will do the first approach. For first, we will put all of them in a single partition. Okay. Now, for S2, for S1, for 0 state, it is going to S2 and the output is remaining 0. Okay. For S2, for both the cases, zeros and 1. For S2, the same thing. For S3, for 1 input, for 0 input, it is going to S4 and producing output of 0, output of 1. That means it is going to final state. And for, oh, I forgot one transition here. And for 1, it will go to S1 and it will produce output 1, output 0 in the next step. So we can readily say that S1, S2 are different for S3 from S3. They can be put in the separate partitions, and S4, S5, S6, these are the final states. They have got the output zeros every time, so they can be put in the same partition. This is the first step. Okay, this is the first partitioning step. Now you go to the second step. What will occur? See, for S1, it will go to, for x equal to 0, it will go to x2. The next state output is also 0. It's not a final state. And for S2, it will go to S1 or S3. with a next state output of 0, but we can see that S1 and S3 belongs to different blocks in the previous step. So we'll just partition them. We'll say that S1 is S1 and S2 are different. You are understanding, no? Now for S4, S5 and S6, you apply input 0 and input 1 and try to see whether it will go to states which belong to some other blocks. Okay, you can see that for x equal to 0 inputs, you will go to always S4, which belongs to this block, and for x equal to 1, you will go to either S5 or S6, which belongs to this block also. So they remain in the same block. There is no distinguishable states in this block. If you go on refining this, you will always get this. So this is the minimum state for these state machines, and we can readily say that these three states can be covered using one single state, one single final state, which has got 0 outputs. Sorry, 1 outputs. Now do for the other using other algorithm. We'll do another page. Okay. So you will compare S1 and S2, and you will see that S1 and S2 are equivalent if S1 and S3 are equivalent. S1 or S3, they will be equivalent if S2 and S4 are equivalent. S1 and S4 are equivalent if S2 and S4 are equivalent and S1 and S5 are equivalent. You can do that, I guess. Okay. Huh? Yeah. Okay. For this case, you can readily say that this is not equivalent. Thank you. This way you can do always. Okay. So that's all about state minimization. See what are the else can do. Oh, I got a slide for a state minimization. I don't know why the slides are coming this way. Okay. These are the main objectives of state minimizations. So I don't know why the slides are coming this way. Actually, I used Office 2007. That's why I don't think. Okay. These are the examples for completely specified machines. And what is completely specified machine I have told in the slide. And use the same example that I just solved here, and here the algorithm is mentioned. These are some theorems about completely specified machines, and this is another example. That's all for logic synthesis.